Okay, so this is our last topic. Before I start talking about these notes here, let's do a quick recap of some of the things you need to know as we go along. First topic we talked about was, do you know terms like homogeneous, heterogeneous? Do you know compounds, elements? Do you know properties like physical properties and chemical properties and physical reactions? And like, do those sound familiar to you? Second day, we talked about safety stuff. We don't do a lot on safety, but if I were to give you some WHMIS symbols, could you recognize them? Okay. There's going to be a WHMIS question on your PAT. I like guarantee it. Right, where they're going to give you a symbol and you have to just know what the symbols are. The good news is, for the most part, like they're almost like intuitive. If I see skull and crossbones, don't drink it. Right? If I see a hand that's corroding into bone, it's probably corrosive. Right? Like they're pretty intuitive symbols. That's topic 2. Topic 3, we learned about a lot of history. Do you know about scientists like John Dalton and his model? Do you know Ernest Rutherford and what he did? Okay. And again, if you're shaking your head no to this, rewatch my YouTube video, right? That's why I have them. Okay. Day 4, we learned a lot about our periodic table and our elements. And I want to do a quick example here. If I were to give you something like this, O, 2 negative, 17, 8, do you know what each of those numbers means? Let's do them right from the beginning. Let's start with this one here. Number 8 is how many protons it has? And it has to be 8, because then it's not oxygen. If it's 9, then it's something else, which is why, by the way, for those of you doing this question, the alchemists could not turn lead into gold, because lead has a certain number of protons and gold has a different number of protons, and I can't just all of a sudden change the surface level. Like, I'd have to affect how many protons there are. The top number here is known as a mass number, and it kind of tells you how many neutrons there are if you subtract the two. Subtract the two numbers, that's your neutrons. You can change neutrons. This number up here tells you about charges. There's 2 different ways you can do it. It can either be an anion, which gained electrons, which is what this guy here is, or it can be a cation, which loses electrons. And hopefully you can kind of interpret that notation as well. This particular oxygen ion has 10 electrons. Let me say that one more time. This particular oxygen ion has 10 electrons. How did I figure that out? Well, there's 8 protons here, which means there should have been 8 electrons. But this minus 2 here means there's 2 more electrons. So 8 plus 2 more makes 10. Okay. If that's something you know how to do, that's awesome. If not, we got to work on it. Okay, that was topic 4. Topics 5 and 6, I think you probably have the least practice on, so we got to find some practice eventually. It is all about, if I give you words or formulas, can you name them? Let me give you a couple of basic examples. If I were to give you CaCl2, or if I were to give you N2O4, or if I were to tell you dichlorine pentaoxide, sure, that's what you said. And let me do one more. Let's do aluminum bromide. If I were to give you these examples, could you do this? CaCl2 is called calcium chloride. N2O4 is called dinitrogen tetraoxide. Do you know how to like go from formula to words? Or if I give you words, can you tell me that this thing right here is Cl2O5? Okay, we got to practice then, that's all. Or for this next one here, aluminum bromide, do you know that aluminum is a +3 charge? Bromine is a -1 charge. Therefore, for them to fit together, the formula has to be AlBr3. If you kind of gave me a little look there where you're like, ooh, I'm not good at that one, that's fine. We got a week, okay? It's not like you have to do this right this second, but now we have some ideas on things to work on. Okay? And tomorrow I'm going to do an activity to hopefully help us work on this as well. Okay? But I need you guys on topics 5 and 6 to be able to know your different compounds and how they fit together. Okay? So here's our last topic, and then hopefully we have a couple of days now to work on them. This topic here is back about chemical reactions, and I want to go back to the analogy I've been using for the last 2 weeks. I have to teach you how to read. Just like I teach my 4-year-old and my 6-year-old how to read, we're doing similar concepts here. When we first learn how to read, we learn our letters, right? Cammie's learning her letters. She does flashcards. She knows that K is K and P is P, and sometimes she gets B and D mixed up because, like, it's hard for a 4-year-old, right? That's your elements. Then my daughter that's 6 is working on words. C-A-T says cat. She's actually starting to work on, like, compound words like pancake or, I don't know, fire hall, right? She's working on those parts there. But after Kinsey learns how to read words, ultimately she has to be able to read like a sentence. Okay? And that's what we're going to focus on today. I'm going to fast forward in my notes to this slide right here. Our goal today is to help you guys be able to put this all together. Okay? And you're in grade 9. This is early. We're going to do this lots over the next few years. But I need you guys to be able to look at something like this and interpret what's going on. This is like reading a sentence. And we're going to start off basic and we'll get more challenging. What we're going to learn is that this is a sentence that says something like this. Sodium chloride, in an aqueous format, meaning it's dissolved in water, has been added to water in a liquid form, and it is chemically reacted and formed a compound called sodium hydroxide, which maybe you're not familiar with this one yet because we haven't done a lot of practice on it yet, and another compound called hydrogen chloride. Good question. So a liquid's a pure substance where there's only one item there. For example, imagine you had just a glass of water. We'd call that liquid. But imagine that you put some Kool-Aid crystals inside the water and you've now made a mixture. That's what aqueous is for. Aqueous is a symbol for mixtures where you kind of like stir them and dissolve them in water. Does that make sense? But liquids if it's just pure by itself. So this is my goal. This is our end game. I need you guys to be able to read and interpret chemical equations and formulas. And again, like you're giving me a look like we're not there yet. That's fine, right? We're building our way up. That's okay. So let's start at the beginning here. Let's do a bit of review. Do you guys remember these words, physical changes and chemical changes? Okay. Just to remind you, a physical change, the components don't change at all. You can undo a physical change. You can melt it or refreeze it or bend it back into place. But a chemical change is something different. And that's what we're going to focus on today is chemical changes where brand new materials are being made. Okay. Now, the words we use are chemical reaction. Okay? So sometimes we use the word chemical change, but this is probably our preferred terminology. We call it a reaction. Okay? It's probably fair to say that we don't have a phrase physical reaction. We call them chemical reactions because something new is made. But like we never really say a physical reaction. That's never really made sense. We call them changes. So the proper terminology from now on will be it's either a chemical reaction or a physical change. That's probably how we'll phrase them. Okay. But like we know that it's a chemical reaction based on this. There is something different. There's something new properties. Now, this picture I have right here, what are some indications that there might be something new being formed? Yeah, the smoke, right? So the steam, the smoke, the gas. Good call. What else? Clayton. Yeah, I think I see some bubbles in here. I don't know whether it started off as a black color, but if it didn't start as a black color and now it is, a color change is a good indication as well. The steam might be heat, which might mean that it's getting warm. Right? Those are all indications of something new. Okay. So that's what I have on this slide right here. You guys need to be aware of what makes something a chemical reaction. And it can't be undone. It's something that makes brand new properties. And like here's a summary slide. Okay. All reactions involve new substances with new properties. They also involve energy changes, meaning they either get hot or they get cold. And you might even see phase changes like gases or bubbles or a solid that shows up. Okay. We've talked about this before, though. This is kind of meant to be a review right now. So these are the defining characteristics of something being a chemical reaction or a chemical change. Okay. This is what's new now. Here's the words we use. The old stuff that you had, the stuff that you had before you changed it, the word we use is called a reactant. That's the chemistry word. So if you want to add this to like a definition list, a reactant is what you start with. And because you're making something new, we have a word for the new item. The new item is called a product. That's the vocabulary we're going to use. Begin with stuff called reactants, end with stuff called products. Make sense? So let me go to that example that I kind of hopped to in advance. This is a good example of what we call a chemical reaction, where we're going to write out like a sentence, so to speak. There's going to be multiple things reacting, and there's an arrow, and they turn into something new. This arrow, let me start with that. The arrow is our way of indicating that there was a chemical change. That's what the arrow indicates. We used to have NaCl and water. Now we have new stuff. The arrow is the way we separate it. It's kind of like a math equation. If you were to say that like 3 plus 6 equals 9, the arrow is kind of like the equal sign. It's what separates the before and the after. In terms of vocabulary, the stuff you start with then, we call these things reactants. Stuff that you begin with is a reactant. And the stuff that you end with, you guys remember the word already? Product. Yeah, that's the word we use. So it's like a sentence. It's your before and your after stuff. Okay. My goal is just to help you become familiar with these a little bit. This is kind of where Science 9 stops, but we do the same thing in Science 10, and it builds in chemistry if you take chemistry in high school. Now, before I go any further, I need to remind you guys of a couple of things here. Although maybe you're not overly familiar with how to name all these things yet, because we're going to practice it more, okay, I want to focus on this one right here, water. H2O. This 2 right here in the corner. Remember what that 2 means? There's 2 hydrogens. Yeah, you kind of said it, so I just hopped in there. Yeah, if I wanted to, I could write it like this, HHO. We would call it a dihydrogen. There's 2 hydrogens. But we kind of we abbreviate it by putting a little 2 in the corner there. I want to remind you about how that works because that's really important on like some future examples here. Okay. I'm going to get to that in a second. Before I get there, I want to remind you about a scientist. We talked about him already. His name was Antoine Lavoisier. And he sometimes is known as the father of chemistry because he was one of the first people who came up with some really important theories, including this one here. It's called the law of conservation of mass. And he basically did a lot of chemistry experiments. He started with something, and he ended with something, and he weighed them. And he discovered that the mass of the products was always the same as the mass of the reactants. If he started with 5 grams, and then he burned it, it always weighed 5 grams afterwards. He discovered there was kind of like a consistency to this. We're actually going to do this tomorrow. We're going to do an activity and trying to prove that when we start with a certain amount, it ends the same way. And I've got a picture slide here to help illustrate the idea. Imagine you did this example here. You took some magnesium that weighed 24.3 grams, and you took some sulfur, which weighed 32.1 grams. Although I don't know why my pictures are different. I think this is 2 different examples here. There's 2 different ones here. Imagine this was 24.3 grams, this was 32.1 grams. However much the initial things add to, that your reactants add to, your products should equal the exact same amount. And if you take your calculator and add these 2 numbers to each other, it should equal this one here. And this picture one is the exact same thing. This is iron and sulfur, 13.9 grams and 8 grams. If you combine them together, it should equal 21.9 because you're basically just adding these 2 numbers to each other. That's the law of conservation of mass. It basically states whatever you start with, you should finish with. Now, Lavoisier proved this with experiments, but I can explain it going back and describing that little 2 number in the corner there. I want to use that to try to explain why this should be true. I've got some pictures here. Okay. Here's an example of a reaction. What we have going on here is this chemical reaction. It involves some oxygen gas in groups of 2, and it involves some, let's go with nitrogen gas. Oh no, that's not going to work. Let's make it carbon. You guys can see that this thing right here, these guys are the oxygen gases right here. See all those ones are coming in groups of 2? And carbon, if you guys remember, can come in groups of ones. And so this one and this one and this one, there's all these ones right here. Okay. And what they're making is CO. And the reason why I know that it's making CO is that there's one C and one O. It's actually making carbon monoxide in this example, not carbon dioxide. What you'll notice, though, is count up everything that we have before and afterwards. There are 1, 2, 3, 4, 5, 6 little white oxygens there. And afterwards, there's 1, 2, 3, 4, 5, 6. And look at the blue carbons. There's 1, 2, 3, 4, 5, 6. Afterwards, there's 1, 2, 3, 4, 5, 6. Whenever you have a chemical reaction, I think of like how my daughters play with Lego. And they used to be playing with some sort of toy. They made like a Barbie dream house, or they made a car or something out of it, right? And then they rip it apart, and they make something new out of it. But like the building blocks that you have there, they're all still there. They're just in new spots. It used to be that these two things right here were stuck together. But it looks like what happens is it's been broken in half. All of these things have been split, and then they've started to find a partner to kind of join to. That's what makes it a chemical reaction. But the stuff that you have, it's the same stuff, just like when my daughters play with Lego. Here's another picture. This is about hydrogens and oxygens combining together. You can see that here there's an H2. Remember how hydrogen is diatomic, comes in groups of 2? And this is O2, and it's making H2O, water. Look at the picture here. Here's an H2, here's an H2, here's an O2, and afterwards it made an H2O. And see how there's 2 hydrogen with each oxygen? But like the same stuff is there. There's 1, 2, 3, 4 of these. There's 1, 2, 3, 4 of these. There's 2 of these and 2 of those. There's nothing new introduced, and there's nothing that's like lost, so to speak. And that's where the word conservation of mass comes in, is that there's always the same stuff there. Now, here's how we have to describe this. Okay. Because of this, this equation right here is not written correctly, though. Okay. It would actually be written like this. I'm going to put a big 2 in front of this guy and a big 2 in front of this guy. Why? Well, look at the picture. Do you see how there were 2 of these hydrogens right here? And there's only 1 of these guys right here. That kind of implies that there's a 1 of those. And it made 2 of these guys. That's why there's a 2 there. Sometimes when you see chemical reactions, you're going to see big numbers in front. Okay? It's kind of like if you guys have started doing algebra, and you get like 2x plus 3x equals 5x, and you have these numbers in front. Have you ever done stuff like this before? They're called coefficients. That's a big part of chemical equations, because it helps keep them balanced. Okay? Here's the exact same sort of picture here. This is what I want you guys to become familiar with. These things are called reactants, because we start with them. These things are called products, because we finished with them. And if you ever see numbers in front, it tells you how many of them there are. Okay. A very common PAT question would ask you, how many hydrogens are there? Let me ask this again, and then I'll answer your question, Tyson. How many hydrogens are there? And the answer is 4. Because before we started, there was 1, 2, 3, 4. And then after we finished, there is still 1, 2, 3, 4. Some kids would think there's 8. Because there's like, well, there's 1, 2, 3, 4, 5, 6, 7, 8. But does it kind of make sense as to why it's not 8? Because, okay, so the question would be, how many hydrogens are there? And if I gave you a picture like this, the answer is 4, not 8. Some people would count and go, hey, there's 1, 2, 3, 4, 5, 6, 7, 8. Not that they're in groups, but this is how many there were before, and this is how many there were after. And it should be the same before and after. We don't have more. They're just in different places. There's 1, 2, 3, 4 before, and there's 1, 2, 3, 4 afterwards. Okay. Now the way I can figure that out, though, is by like drawing out this picture right here. This 2H2 means that I have an H2, like here's a group of 2 hydrogens, but I have 2 of them. This right here means I have a group of 2 oxygens, but I only have 1 of them. And that's what I want to get out of this lesson today, is if I give you an example like this, can you tell me how much of everything there is? Okay, Tyson, you had a hand up. Do you still have your question? Okay. Okay, let's try an example here. Hypothetically, let's say that they gave you an equation on some sort of test that looked like this. Okay. I need for you guys to be able to interpret what it means. So I like this slide I found on the internet because I think it helps. This CH4 right here means that you have 1 carbon and 4 hydrogens. CH4. Look at this picture here. There's 1, and then there's 1, 2, 3, 4 around it. The next thing it says is that you have 2 O2s. Okay. Well, first of all, the big 2 right here, what does that mean? Well, it means that there's 2 of these things. Okay. Then the O2 means that they come in packages of 2. So this has got 1, 2, 1, 2. How many oxygens do you have, though? 4. Then there's the arrow. This is my daughter taking her Lego toys and rearranging them. Or maybe a better example, she likes Barbies right now. And so she takes the head off of one Barbie and puts it on the other Barbie, and she takes the clothes off of one and rearranges them. She still has the same stuff, but now it's been rearranged. Right? So now look over here. Now you have CO2, carbon dioxide. What does it mean? Well, if you don't write a number in front, it means there's 1 of them. So that's why there's only 1 molecule here. And there's 1 carbon, and your O's, there are 2 of them, hence the CO2. Over here, see how there's a number 2 in front of it? Why is there number 2? Because there's 2 of them. Right? What's the molecule of? Water, H2O. Well, that means you have H twice and O once. H twice and O once. And if you look at the math, you started with 1 carbon, and you kept 1 carbon. You started with 4 hydrogens, and you kept 4 hydrogens. And then for the oxygens, you started with 4 oxygens, but like, compare these ones over here. Isn't 2 plus 2 going to give you 4? So a very common question would be this. It would be numeric response. And it would ask you, how many do you have? And they would say something like this. How many carbons do you have? How many hydrogens do you have? And how many oxygens do you have? And the correct answer would be you had 1 carbon, you had 4 hydrogens, and 4 oxygens. You had 1 of these, 4 of these, and 4 of these. Don't make it 2, 8, and 8. Because that means you're counting what you started with and what you finished with. Don't double it by accident. Does that make sense? Okay, we're going to practice this, okay? I'm trying to talk to the whole group at once here, right? But like, that's why we have assignments and quizzes and projects to work on. Okay, second half of my lesson. I need to describe to you guys some properties of reactions. Okay, you're expected to know some more terminology, some more definitions. So my remaining slides are basically all about some terms. Here's the first one. I need you to know this word. The word is called exothermic. Exothermic. And the way an exothermic reaction works is it's any reaction that gives off energy. Like if you light something on fire, that would be considered exothermic because you can clearly see that there is light being like given off. Anything that you burn is a great example of an exothermic reaction. Okay? Here's how I remember this one, by the way. Exothermic is kind of like the word exit, which means that like something is exiting the system. Like in a way, like light is being exited out, right? Like you're producing light. Okay. That's called an exothermic reaction. But there's actually an opposite to that. So if you want to flip over to your next slide, the opposite of an exothermic reaction is called an endothermic reaction. And rather than giving off energy, this one needs to absorb energy. A classic example is like a cold pack. Okay. What's really happening when a cold pack feels cold is it's sucking the heat out of you. Okay. Why do you put a cold pack on your knee when you sprain your knee or your ankle? Anybody know? Like, why do you actually put cold on it? Yeah. That's the word I was looking for. Good try, but yes, it slows down the swelling. Okay. Now, how does it slow down the swelling? Well, you know what it does? It literally sucks the heat out of your ankle or your knee. Now, when heat gets sucked out of your knee or your ankle, we feel it as cold. But really, there's no such thing as cold. Cold, you just feel cold when heat is leaving your body, right? Say it's minus 40 outside and you walk outside without a shirt, without a coat. You should wear a shirt at least, right? You should wear a coat. But like if you feel cold outside, you're actually feeling the heat literally leaving your body. Does that make sense? And so if something is like absorbing your energy and sucking it away, then that is an endothermic reaction and it feels cold. Whereas on this example here, if you were to stand around a fireplace, if your body is rather than losing its heat but gaining more because you're going, ooh, toasty warm fire, that's an exothermic. Okay. So 2 words I need you to know, endothermic and exothermic. I remember this one here because this is like the word enter. So it starts with N. Exothermics have an energy exiting. Endothermic is where you're absorbing energy. Okay. So the cold pack is absorbing your energy when you put it on your ankle, which is good though, right? Because that's how it prevents swelling. If it sucks the heat out of you, then then you can't swell as much. Okay. So that's basically what this slide here refers to. I need you guys to then know this vocabulary. Exothermic reactions then get very hot. Endothermic reactions then get cold. That's basically how it works. This heats something up because energy is exiting. This is causing energy to be like soaked up, entering the system, and then cooling something down. Does that vocabulary make sense? Okay. So let's talk about a couple of reactions. Let's see if you can figure out whether it's exothermic or endothermic. Your car. Do you think it underdoes exothermic or endothermic reactions? So you say endo. Anybody else want to take a stab at it? Is your car an exothermic reaction or an endothermic reaction? So let's consider underneath the hood of your car. Does the hood of your car, like your engine, does your engine get hot or cold when it runs? Yeah. No, because if it gets hot, it's exothermic. You have it backwards then, Tyson. Okay, and the reason why is that your car is producing energy and it's producing heat in the form of like combustion in terms of friction. So your car is actually going to get warmer. It's going to exit the system, and we use that energy. Okay. Now I've already used the example of a cold pack, so I won't use that one again, but let me try a different one. Photosynthesis. Have you guys ever heard of photosynthesis before? It's where a plant uses light from the sun to grow. That one would be endothermic. And the reason why is that the plant is literally sucking up energy in the form of light from the sun. And it's like soaking it in. Does that make sense? So one is like, soaks in, and the other one is like expelling the energy. Okay, now there are actually 4 reactions that I need you guys to know even more about in terms of like vocabulary. 4 common ones. Okay? So I need you guys to memorize these. You're probably somewhat familiar with them, but let's talk through them one at a time. The 4 that you need to know for your PAT for sure are combustion, corrosion, photosynthesis, which I just mentioned, and cellular respiration. Okay. Let's talk about them. Combustion is what I just talked about in your car. Whenever something is like blowing up or burning, like when you use your car, you are burning gasoline, right? If you're burning something, it's probably giving off energy. Okay. Now, you don't need to memorize this reaction, but this is the chemical reaction going on inside your car. Okay. Now, what I need you guys to be able to do is, could you tell me something like this? How many oxygen is being used? Could you look at this equation right here and tell me how many oxygens are being used? Okay, let me help then. I'll tell you the answer. The answer is 38. Let's talk about why. Do you see any oxygen in this thing right here? Okay, let's focus on this guy right here. There's 19 groups of 2. What is 19 groups of 2? 38. Yeah. Now, some people would look at this and say, but hang on, there's more oxygen right there and more oxygen right there. But it's the same ones, right? They're just the ones that they've turned into. Okay. So this is what you started with. This is what you finished with. So, I mean, I could count up all the ones on the end. What you actually have here is 12 groups of 2, which is 24. And here you have 14 groups of 1, which is 14 more. 24 and 14 actually does that up to 38. Okay. So that is a question I could ask you. Or I could ask you, do you know what combustion is? And combustion is basically whenever you blow something up, and set it on fire. And if you don't know this already, there are 3 things required for any combustion reaction. You need to have a fuel source, which would be like your gas. You need to have air, because you always have to have oxygen to burn something. And then finally, you need heat, like a spark, a match to get it going. Okay. So that is one type of reaction that hopefully you're kind of familiar with, blowing something up. Second reaction. It's called corrosion, but you guys are probably more familiar with its common word, rusting. Now, rusting is often used specifically to talk about iron. So corrosion is kind of more of a catch-all word because corrosion refers to anything that's a metal that kind of like rusts. But like rust usually refers to iron specifically. Like for example, these chains right here, you guys have seen rusting before, right? Where it turns this like reddish kind of looking color and it kind of flakes away. Right. So here's what I need you guys to know about corrosion. Corrosion is an exothermic reaction as well. This is also exothermic, and the reason why I know this is that energy is being like released. See how energy is like on this side over here of the equation? It is being produced. We are producing energy when we do this. Okay. And one more thing I need you to know about corrosion is that it also involves oxygen. You need air for things to rust. Okay. So there's some similarities there. Both of these 2 reactions are similar in that they both involve oxygen and they both produce energy. But not everything produces energy. For example, our next example here actually requires energy. You'll notice this time that light is actually on this side of the equation. And the reason why it's on this side of the equation is that when plants grow, it requires light. So rather than it being like sent outward, it actually needs to be sucked inwards, just like my picture has, right? Like light needs to be absorbed by the plant. And so this is known as an endothermic reaction. Now, the way that this one works is that plants use light, carbon dioxide, and water, and it makes sugars. This molecule right here is a sugar. One more interesting thing, though, just like the previous examples, it also involves oxygen. Plants actually make the oxygen that we use to breathe. So that's a third reaction hopefully you know a little bit about. The last reaction is known as cellular respiration. And this is what we as humans do when we eat. You hopefully have eaten something recently. Maybe not this morning. Hopefully you had breakfast. But hopefully you've eaten some food. Okay. Well, you also breathe in oxygen gas. This would be sugar, and this would be oxygen. And when you combine in your body the oxygen that you breathe and the food that you eat, it provides a few things. First of all, it gives you energy. Now you notice again, energy is now on this side of the equation, a product, meaning that we now have energy that we can then expend and use. Right? But what else does our body produce? Our body also produces carbon dioxide, which is why when we breathe in and we breathe out, it actually does different things. When you breathe in, you're breathing in oxygen. And if you didn't know this, when you're breathing out carbon dioxide. Okay? And one more thing, your body also makes water, which is why we go to the bathroom, right? Regularly, you need to pee, right? Because your body is like 75% water. Okay? And so this is the formula called cellular respiration. Okay? Of those 4 things here, I need you guys to be familiar with all 4 of them and know some similarities and differences. Almost every single one of these reactions is similar, Seabass, stay with me, in that they all involve oxygen. This one involves oxygen, this one involves oxygen, this one involves oxygen, this one involves oxygen. They're all similar, they all involve oxygen. Other similarities, these ones right here were all exothermic reactions, but photosynthesis is endothermic. Combustion gives off energy. And when you rust some metal, it also gives off energy. And when you eat food, it gives you the energy you need to do stuff. But plants need to soak up energy. There's the difference. So somewhere on your PAT, I don't know exactly how they're going to test it, but they're going to want you to know about those 4 reactions. Okay, so be aware of how they work. Okay. Last slide, and then I'm done. The last thing we want to talk about is rates of reaction. And a rate of reaction talks about how fast a reaction takes. Some of the reactions that we talked about here are slow and some are fast. Okay? For example, cellular respiration. When you guys eat and breathe, that happens almost instantaneously that your body gets the energy it needs. How long can you go without breathing? Yeah, about 2 to 3 minutes, give or take. Depends on the person. Okay? But if your body stops getting oxygen, you're going to die, which is why those have a very fast reaction rate. Okay? Combustion, when you blow something up, it takes seconds, less than a second, for something to go whoosh. But there's other processes that are very slow. For example, photosynthesis. Let's say that you took a plant, and for some reason, I don't know why this would ever happen, but let's say that that the world went dark for, let's say, 12 hours at a time. It's called nighttime, guys. Does the plant die just because it goes dark all of a sudden? No. Now, humans, if I couldn't breathe for 12 hours, I'd be in trouble, right? But that's because photosynthesis is a very slow reaction rate. It happens over a longer period of time, which is good because when the sun goes down for 12 hours, the plants don't die. Right? Corrosion, rusting is also a very slow reaction rate. Okay. So the last thing I need you guys to know are that there are 4 factors that affect how fast a reaction can occur. Here are the 4 factors. One is called the concentration of reactants. One is the temperature. One is the surface area. And the last thing is something called a catalyst. Let me talk about all 4 of them, then we're done. First one's concentration. What concentration really refers to is not whether you're paying attention, because hopefully you are right now, but concentration refers to like how much of something you have. Okay? If you have a lot of something versus a very little amount, that affects how fast something occurs. For example, let's say that you had lots of sunlight and you had lots of water. As a plant, it would actually react a little bit quicker. But if there was no sunlight and no water, it would slow down. I'm going to close that door because that's distracting me. There are some people that I can actually slow their heart rates down. I don't know how to do it myself, but there are some people who can actually slow down their heart rates and make their body run slower. Okay? The reason why you might do that is because you don't have oxygen to work with, or maybe you haven't eaten in a long time. I don't know why. Okay? But that's concentration. The more you have, the faster it will react. The less you have, the less fast it will react. Seems obvious. Second one is temperature. And to talk about temperature, I want to discuss the picture on that slide there, the freezer. Guys, stay with me. I'm almost done. Bread can mold. You've probably seen this before, right? You leave bread on the counter for a couple of days or weeks, and it starts to go moldy. But if you put the bread in the freezer, it doesn't. Why? Well, it's about temperature. When we freeze things, we slow down reaction rates. They happen slower. We put meat in the freezer as well, so it doesn't go bad. Long story short, the lower the temperature, the less quickly the reaction takes place. Let me give you another reason why this matters. In Canada, in the wintertime, if it's minus 40 out, sometimes our cars don't start. The reason why our car doesn't start is that the chemical reaction getting your battery to start to work, to like turn over the engine, it can't work very well in the cold because the reaction rate is too slow. Okay? Things usually work better when it's warm out. We actually know about this already. In our first unit on biodiversity, we talked about how there's more diversity at the equator than there is in the Arctic. And the reason why is that it's warmer in the equator, right? And because it's warmer, more chemical reactions can take place, which is why there's more diversity there. So that's factor 2, temperature. Factor 3, surface area. I want you to imagine that you need to chemically react to something, for example, food. Your body uses food in a chemical reaction. You know what we do as humans to help speed up the reaction? Is we chew it. And by chewing our food, it makes it go down our esophagus a little bit easier. Girls, focus. But it also breaks it up and gives it more surface area. It like makes it into smaller pieces. If you have smaller pieces, it can like react quicker. If you have really big pieces, it's not quite as easy to use. Does that make sense? So chewing our food is one of the best examples I have of that. Okay? And maybe I can kind of draw a bit of a picture to help illustrate it. So give me a second, I'll draw a picture. Imagine that you had this big chunk that looked like this, one big box. Or you had a whole bunch of smaller pieces. So imagine that at the end of the day, I have all the same amounts. Okay? And imagine a chemical reaction wants to take place. Well, only the very outside of this box can react. And everything that's in the middle is kind of protected. And slowly but surely it would wear it down and wear it down until it reacts. But if you chop it up into little bite-sized pieces, well, now it can react on the outsides, but now it can also get through and react on the insides as well. So surface area basically means if you grind it up, it works better. Okay. Okay, the last one. It's hard for me to describe this in grade 9, but the term is called a catalyst. And basically the way the catalyst works is it is an extra chemical that we add to speed up a reaction, to make it work better. Okay. I actually used a catalyst in one of our labs. Maybe you don't remember it, but it's the elephant toothpaste one. It was where we made the soap really bubble up over the top of the test tube there. If you remember that one. I used a catalyst in that to make it happen faster. Because if I just combined the hydrogen peroxide, it would have taken like days to occur. And so I added an extra chemical in called potassium iodide. I would have described it at the time, but I'm not even sure you remember it. Okay. So a catalyst is a chemical that just makes things go faster. Okay. Let's memorize those 4 factors. And that is it. That's chemistry. Okay. So a couple of passing thoughts, then you guys can take off. Okay. First thought, I need you guys now to do some practice on this. Okay. I've spent 7 days talking at you. I do not believe that you should understand it just by me talking at you. Okay. I'd like to hope that you're on a good start, but you need practice. Okay. You need to finish up your assignments. There's 2, and your labs and activities. Okay. And through doing that, if you do that, hopefully I can help you build the skills you need. Okay. We're going to do a quiz on Thursday. It's a practice quiz. If you don't do well on the quiz, no big deal. It's just for practice. But hopefully we'll learn from it as well. Okay. In the meantime, you guys have some practice time to work on things. Now, I got to point out one thing that I've noticed a little bit here. I'm allowing you guys to redo any and all tasks. There is a difference, though, between redoing a task and copying off of your friend who got 100. Okay? I've noticed it a little bit. Don't do that, because that's cheating. It's literally happening right now as I'm talking to you about it. Okay. Guys, I'm very willing to give you guys the answer keys. Okay. I'm going to trust that this is about learning. Okay. But please don't ever put yourself in a position where you're copying and cheating. That's not what we're going for here. I will help you all you need. I will give you an extension if you need. But like literally putting 2 pieces of paper side by side and that's not learning, guys. Okay? I need you to try this by yourself in order to grow and get better. Does that make sense? Okay. So we've got a week. Okay? I'm now done teaching you chemistry in terms of big group stuff. But you need to practice and try things. Okay? Does that make sense? So the answer key to the first assignment is on the board. In theory, you could cheat. You could. You could take it, the answer key, put your assignment next to it, and just copy it down word for word. That's not a good idea. I mean, yeah, you'll get a good mark, but you're not learning. And I want you to learn. And 2, I got to remind you guys, if I do catch you cheating, and like it's very blatant and obvious, I've said that I have the right to make you redo everything you've done all year. Okay? I don't want to have to make you redo all of your biology assignments now. Okay? So don't copy off your friend. Okay? Do it honestly. And do it with the purpose of you learning, because that's what I want. I want you to learn. I don't want you just to get a good mark. Hopefully you will get a good mark. But if all you need is like a 90% or a 70% to get your parents off your back, I have higher aspirations than that, guys. I want you to do well. I want you to learn. Okay? Does anybody have any questions? Okay. You have 20 minutes today, guys. So use the last 20 minutes to get started on stuff. Tomorrow we're going to do an activity. Wednesday's work time. Thursday is a quiz. Okay, I'm done. Come ask me questions as you need.